Mr. Monahan here for Prob and Stats Lesson 2.7a. We're talking about two-way tables and conditional probability. That is our goal, that we can calculate both of those things, conditional probabilities and probabilities from a two-way table. Conditional probability is going to be a little familiar. We talked about this with the independent-dependent day when we were multiplying different events. Conditional probability is the probability of an event if we already know or given that another event has already occurred. So this is kind of a dependent situation when we're talking about probability. There's just a little bit less multiplying today. Remember that this symbol right here, this vertical bar, is looking like our given sign. So it's the probability of B given A. So that bar means given. So we know that the probability of B is changed based off the fact that we know for 100% certain that A has already happened. Here's an example. A single card is dealt from a deck of 52 cards. Okay? We want to find each conditional probability. So we want the probability that we get the two of clubs. So not two different clubs, the two of clubs, given that the card is black. So normally, if we wanted the two of clubs, there would be 52 cards, only one of them is the two of clubs, okay? But since we know that it is going to be a black card, we have to think about how many black cards are there, half the deck, okay? Half of the deck is black, half the deck is red. So there are 26 black cards. Only one of them is the two of clubs. So what happens is the thing that's after the given, whatever's after the bar, is the denominator. So however many things there are after the given bar, that is what goes in the bottom of the fraction. So if I want the probability that the card is black, given that it's a diamond, well, first we want to figure out how many diamonds are there. Diamond is a suit, so there are 13 diamonds, okay? But diamonds are red cards, right? Diamonds are red cards. So how many of the diamonds are black? 0. So this is 0%, or just 0, okay? The probability that we get a queen, given that it's a face card, so the first thing we want to figure out is how many face cards are there. There are 12. There's 4 jacks, 4 queens, and 4 kings. Okay, so of the 12 face cards, we want to know the probability that we pick up a queen. So this is saying, I know that I picked up a face card. What's the probability that it was a queen? Well, there are 4 queens in the deck, 4 of each card. Okay, so this reduces to 1/3 or 0.333 or 33.3%. So whatever is after the vertical bar, that means given, that impacts the bottom or the denominator of the fraction. Whatever's to the left of the bar, we just say how many of those are there. Part B was kind of a trick question because there won't be a black card given that it's a diamond. Okay, so let's look at a different example. If you were here today, we would be asking this question. What's the probability that you showered this morning? And we'd be looking at, is there a difference between boys and girls in this scenario? So I'm just going to make some numbers up. Normally we would actually poll the class here. Let's say that I asked all the boys in the class who showered, who didn't. Maybe we had 11 guys that did shower, and maybe we had 6 that didn't. Okay, for the girls, maybe we had like 14 who didn't, and maybe 5 who did. Okay, so what would happen is, I'm going to actually put those same numbers in this next one. I'm sorry. So we had 11, 5, 6, 14, because you need another piece of information on the front of that page. So I got a little bit ahead of myself. Sorry about that. The first thing is two-way table. Okay, And that's what I just have filled in here. It's a table used to display multiple events and all of their outcomes. Okay, and then I'll pop up mutually exclusive here at the same time. This is a review word, 2 or more events that cannot occur at the same time. Can't have both. And we'll go through this table. There's 2 different mutually exclusive events in this table. Okay, if you need to pause to write those down, then you go ahead and do that. At the top of the next page is where you'll find this table. Just fill it in with my fake numbers, 11, 5, 6, 14. Okay, so here's how two-way tables are going to work. And we'll do this example and then one more, and then that should be plenty. There are 2 mutually exclusive events in this table. So there's 2 pairs of things that can't happen at the same time. One of them is male or female. You're not going to be both. And one of them is shower or no shower. There's no way that you both showered this morning and didn't shower this morning. You either did or you did not. Okay? So here's how probabilities in a two-way table are going to work. Okay? So the probability that we pick somebody randomly and they are a male, well, here's what we got to do first. After you have the numbers in there, 11, 5, 6, 14, what we want to do is start to get some totals. Okay? Because if I add things down, 11 plus 6 is 17, 5 plus 14 is 19. So I know in this class there was 17 males and there was 19 females. If I want to get the total number of people that showered, for example, it would be 11 plus 5, which is 16, 6 plus 14, which is 20. What you should notice is if you total up 16 plus 20, you get 36. If you add up 17 plus 19, you also get 36. So here's what's happening in this table. 36 is the number of people in class. Okay, so that's going to be the bottom of my fraction, unless I see a given somewhere, which we'll get to in just a minute. Okay, so out of the 36 different people in the class, I need to know how many of them were males. Well, that was 17. The male column, if I add those down, that's 11 plus 6. So there are 17 males out of the 36 people in the class. That is a simplified fraction, so I don't need to get a decimal for it. It's going to be really close to 0.5. Looks like 0.472 if you wanted to put a decimal to it. All right, female will be not much different. Out of 36, the number this time is 19. There's 19 females in the class out of 36. This would be about 0.528. Okay. Unless we see the word given or the little bar that means given, we're not going to have to worry about much else. So what that means is unless I see the word given or the bar that means given, the bottom of my fraction will always be 36. So out of 36 people, how many people showered in the morning? Well, that is this number right here. That's the males plus the females that did shower. So that's 16 out of 36. If I wanted to do that as a simplified fraction, it would be divide by 4. Divide them both by 4, so 4 over 9. If I wanted the decimal for that, it'd be 0.444 repeating. The people that are showering in the morning and male, normally and means multiply, okay? Not with two-way tables. With two-way tables, and is just one very specific box. Where are the males that did shower? Here's the males that did shower. 11 of them did, 6 of them did not. So it's not given that it's a male, it's just showering in the morning and male. So I could still, the females are still part of the population, which means there's 36 on the bottom. There's only 11 people that end up going up top, because those are the people, like I said in the table here, the people that are male and showered. Okay, the 6 below it is the number of males that did not shower. All right, let's get a decimal for that. 0.306, 30.6% chance. Okay, now we have a given. Showering in the morning, given, or that bar, that they were male. So this is almost the same problem. But if they say given, whatever's after the given becomes the bottom of the fraction. So we need how many males there are, which is 17. Okay, that becomes the bottom of our fraction. Whatever's after the given is the bottom of the fraction. So the people that showered in the morning that were male, it's kind of like I'm only looking at this column now. Okay, out of 17, 11 of the people showered. 11 of the males showered out of 17. So that would be 0.647. We'll do one more example with this, and then I'll let you get started with your own. So, good idea for the very first thing you should do, get totals of everything. So take a second, and we're going to add all of the columns down and all the rows across to make sure that we have every number that we need. So I would start doing that right away. So when you do this, you are double checking that the rows add up to the same total that the columns do. So if you add up those bottom ones that I have there, we end up with 1,626. We hope that we get the same thing when we add the rows across, because then we know that we have added everything up correctly. Okay, so the last one we have is adding up that row of males across the bottom. And it's just a good idea to make sure that 856 plus 770 is also 1626. So before you do anything else on this assignment, that might be the very first thing you should do, is just add all the columns down, add the rows across, make sure they get to the same answer in the corner. So we know 1626 is the bottom of our fraction unless we see given. Either the word or the vertical bar. So the probability that somebody has a master's degree, well, it didn't say given anywhere, so I'm going to automatically put 1626 on the bottom. So now I have to figure out how many people had master's degrees. Well, it doesn't say female or male, so I'm going to combine those two. Here's my master's column, so there's 365 people that either male or female that had a master's degree. So since 1626 is a pretty big denominator, I'm not going to spend time simplifying the fractions. I'm going to go straight to getting a decimal, rounding to that third place. Okay? The probability that they're female, again, the word given is nowhere to be found. So I just need to find the female row and the number which represents the total number of females. So there's 856 females. There's 1,626 people total. So that would amount to 0.526. All right, remember and problems, they're talking about a specific box in the table. So and does not mean multiply today. 1,626 is still the bottom because we don't have the word given. So we need to find the master's degree and female number. Okay, 194 is where the female row intersects with the master's degree column. So 194 females have a master's degree out of 1,626 people. That's 0.119. Male and female, that is one of our those are both of our rows. So that means that these are mutually exclusive events. which means they cannot happen at the same time. So there's exactly 0 people in this chart that are male and female, so 0%. Those are mutually exclusive, okay? Same with the next one, bachelor's degree and master's degree. Well, it's the highest level attained. So these 2 columns are mutually exclusive. So if it's an and problem, and they give you 2 different columns or 2 different rows, those are set up in these two-way tables to be mutually exclusive. So that means the people with the if their highest degree is master's, then it also cannot be bachelor's at the same time. Maybe they have both degrees, but only one of those degrees, the master's, is their highest degree. Okay? So now we are into the given stuff. So remember that this bar means given, which means the second number is the denominator of the fraction. So I got to do some scrolling, it looks like. So what I need is the total number of females, which I've already gotten once, 856. There's 856 females in this study, which means that has to be the bottom of the fraction, whatever is after the given. I'm going back up to the chart to see of the females, so I'm only looking at the female row. So you can imagine it kind of like this. The only numbers that matter are the female row. Okay? The males do not matter at all right now. So I'm looking at masters given that they are female, so it's this same 194 again, but this time it's out of 156. So there's 194 master's degrees given that we have selected a female. So that comes out to 0.227. Okay? A master's degree given that they're male. Okay, that's not too bad. So given that they are male, we need the number of males, which was 770 right here, which means we're only looking at the bottom row this time. So there's 770 males. That's the bottom of my fraction. The top of the fraction is the number of males that are in the master's column. So 171 males have a master's as their highest level of education. So the number of 171, right? Yes. The number of males that have their master's is 171. Okay, that's also 0.22, but it's 222 this time. Okay. This one is a given again. So I need to look at how many doctoral degrees there are. That's this column. So there are 42 doctorate degrees. So that is how many there are. That's what's after the given. So that's the bottom of the fraction. Up top, how many of the females, or how many of the doctorate degrees were female? 16. So 16 divided by 42 is this probability, and that one comes out to 0.381. Male, given that they have a bachelor's degree, so I'm going to look for the bachelor's degree column, that's 1145. That is the number of bachelor's degrees. That is also the denominator of this problem. And then I have to look in the bachelor degree column, how many were male? 529. So 529 of the bachelor degrees were males, and that's divided by 1145, so 0.462. Okay, these last ones are OR problems. You have to remember with OR problems kind of how some of this stuff can work. OR does still mean add today. Okay. With these ones, I need to look at first. each individual situation. So the number of males and the number of doctoral degrees. Okay? Remember that we had overlapping and non-overlapping events. So first, I'm going to look at the number of males, which again was 770. Okay? The number of doctoral degrees was 42. Okay? So the probability, so this is not a given problem. So we're back to the big numbers, 1626 for this situation. Okay? The number of males was 770. So there's 770 males in this study. There was only 42 doctorate degrees in this study. But here's the thing. Do these overlap? Is it possible to be a male and have a doctorate? The answer to that is yes. This is a non-mutually exclusive problem, which means there is overlap, which means we need to subtract how many people were in both categories. Okay? So we need to go to the chart and we need to find the number of males right here, the number of males that have a doctorate. This is the male and doctorate part of the chart. Okay, so there's 26 people that got counted twice. I need to subtract this 26 back out. Okay, we have to subtract the overlap if there is overlap. That's great OR problem review. So we have basically 770 plus 16 if you do the 42 minus 26. So this should have a grand total of 786 divided by 1626, which is 0.483. If there's overlap, you have to subtract. Here's one that will not have overlap, and I'll show you why. So again, OR means add. 1626 is the bottom because these are not given problems. But these two are both levels of education, which means these ones are mutually exclusive. We have two columns here. Okay? There is nobody in both of these groups. They are mutually exclusive. So there's 74 people that had a professional degree and 42 that had a doctoral. So I'll do the 42 first because that's the order that they went in. And then I already forgot that number. 74 people that had a professional degree. We do not need to subtract anything because there is no overlap for this problem. There is no overlap. So we just need the 42 and the 74 to add together to 116 up top, 1626 on the bottom. Let's get a final answer for that, 0.071, 7.1%. So the OR problems, you do have to do it the way we talked about earlier this chapter. Is there overlap? Is it possible to be both a male and have a doctorate degree? If you can be both, you have to subtract how many people are both. That's it for today. I believe these homework problem pages are wrong, but you can go into the purple homework packet, look for 2.7a, and you can begin your work. Thanks for watching.